Okay, so we're going to start with a simple Verilog module, and Verilog is a hardware description language used to describe hardware. We can visualize this module here. So this is the actual hardware that we have created here using this code. This is a simple counter. It takes an input, a clock signal. It has a output compare 1 and output compare 2. We're going to be using this output compare registers for generating a PWM waveform out of this counter. We have also auto reload register where we will put the reload value, and we have the outputs as the count, the number of counts so far, the output compare number 1 output and output compare number 2 output. We have an initial block here that defines that we set the count to 0 as an initial count, and we can also actually set OC1 out and OC2 out, but I'm going to do that in the source file. Then we specify what we want to do at every positive edge of the clock. So when the clock goes positive, we want to add 1 count to the counter, and we want to also reset the counter when we get to the auto reload value. For the output compare outputs, we compare the OC1 and OC2 to the count, and if OC1 is more than the count, then we set the output compare to 1, otherwise we set it to 0. So the result of this is that we get a PWM waveform. So normally we can compile this code into like an FPGA, for example, FPGA image, and load it into FPGA. But today we are going to be just compiling it into C++. And the way to do that is by using Verilater, which is a tool that can compile Verilog into C++. So we can generate C++ code from this Verilog code. And what we get is a number of files in the obj.dir directory, which is basically generated code for this counter. As you can see, it's basically using the input variables and generating output variables based on some really hard to read code. What we need to worry about is simply the interface to this counter. And the way that we interface with it is we simply include this vcounter.h file from the obj.dir. So we got a generated vcounter.h, and this object is going to have the inputs and outputs, the input and output variables, which we can access directly. So if we create our C++ program, we then have a vcounter pointer here, which we're going to initialize to create a new vcounter object, which would be represented by the generated code, which was generated from Verilog. Welcome, Benny. Once we have created this this object, let's go down here. And here we create this object vcounter using the new operator. Once we have created that object, we can access this object directly, and we can set the clock to 1, then evaluate the circuit, then set it to 0, evaluate the circuit, and that's basically 1 clock cycle. So how can we use this simulated hardware and allow other applications to access it? What if we were to run this hardware as a separate process that takes care of its own timing? It has its own clock, and it just clocks the timer, and then we just use that timer as a virtual device from another application. And we can do that by we can take care of the timing using Linux timers. And we can take care of the access to this virtual hardware using shared memory. And that is what I'm going to show you today. So this session is going to be about embedded Linux programming, where I show you how to set up shared memory and how to set up Linux timer. That'll be the two main things. And then once we have done that, then we would be able to access our counter from a client application. And the way it's going to work is like this. So we're going to run our server, which will run the counter. So I'll run it right here in the editor. You can see it down in the corner. And then I will run the client for the counter, which is another application which will simply configure the counter and read out its values. So as you can see here, the counter is counting, and it's set to count about 1,000 cycles per second. That should be pretty exact because we're using a real-time clock and we are using a Linux timer. And you can see that the output waveform is I've set one of them. I've set the auto reload value to 1,000, so it counts to 1,000, that resets. And I've set the first PWM output to be half of the period, and the other one to be 250 counts. So one is 500 counts, the other one is 250 counts, and the full span of the counter is 1,000 ticks. So how can we have one program in Linux share an object and then have several other programs use that object as though it was in their own memory? Well, for that we can use a Linux shared memory. And the way this works is that we create a shared memory object. Can everybody see my screen, by the way?
Yes, Martin, yes.
Awesome. So I'll open this file. We have this file and we have this file. So the first thing I will do is create an abstraction for this shared memory object. So we're going to share memory between two processes, and so I want to abstract that away into a shared object, which we call vCounter. So struct vCounter is going to be our shared memory object. So inside this object, we will have variables. We will have the output compare 1 and 2. We'll have output compare output 1 and 2. We'll have the count, and we'll have the auto reload value. And we want to have these values updated from our simulated hardware on the server side, and we want to be able to read these values on the client side. So we're going to have to synchronize this with the actual simulation, and then we also have to synchronize access to this area between processes. If we were to just write these values, so keep in mind that this is shared memory, so when we write the value in one process, the other process can see the change right away. So we have to synchronize accesses to this shared memory. And to do that, we have to use a semaphore. So we'll have a semaphore inside this shared structure, and this is going to be a shared semaphore. So when you create the semaphore, when you call sem init on the semaphore, you have to also set the p shared flag so that this semaphore will be shareable between processes. And then I define a simple API for this vCounter. So we'll have a vCounter new, which will create a new vCounter destroy, that's going to just deallocate all the resources. vCounter get count will return the current count of the hardware. vCounter get OC1 output will return the PWM outputs 1 and 2. And then we have interface for setting the output compare register and setting the output compare register 2 and setting the reload value. And then we have the implementation. So when we want to share something between processes in Linux, we use something called POSIX shared memory. And there is a system V shared memory interface as well, but POSIX interface has replaced the system V interface. The system V interface is the older interface. And POSIX interface has replaced that old interface. And when you use POSIX interface, you'll be using functions shm open for opening a shared memory resource, and then we'll use mmap to map that resource into the current process memory. So when it comes to shared memory resources, what we get is basically, I'll show you, for example, if I start this counter server now, and I can then list the shared memories. So you can see that in dev shared memory, I have a file called vcounter. So this is the file that I've just created when I started the server here. This file is created when I call shm open. And on the server side, I also supply here an argument to tell this code to create this file. So we're going to set this to true on the server side, and we're going to set this to false on the client side. So if we are on the server side, so we want to create this shared resource, so we call shm open with vcounter as the first argument, which is the shared file. It's the named resource. Then we want to create this file, and we want to create it in an exclusive way, so that if you have multiple processes trying to create it at once, we want just one copy to be created. So we create this file, and we also set the read-write attribute to this file so that it can be read and written. And also then, since we have just created the file, we have to also call ftruncate. So if you don't call ftruncate, your mmap will fail, because by default, the region is size 0. So we want to initialize this region to be of size of the struct vcounter, because that's going to be our shared data, which we're going to be sharing between processes. And then you on the client side, it's a little bit simpler. There we just call shm open with a read write, and then we just open this shared resource. So after we have opened the file, we get a file descriptor called fd, and we need to now map this resource into the memory space of the current process. So for that, we use mmap, and we're mapping a file descriptor. So we don't pass any first argument to mmap. We tell it the size of the region we want to map, and we tell it that we want to read and write this region. If we have created the file without correct permissions, if we specify just read here and then try to write to this region, then we will get a segmentation fault. We also specify that we want to map a shared region, and we also specify the file descriptor, which represents this region, this shared area that we want to map into our current process. And then we get our shared region created here, and we can initialize it. So we should probably also check if self is null, in which case it failed. So then we return null, so we don't get a segmentation fault. But once we get past this, we have first we initialize the semaphore, and seminit takes the semaphore object as the first argument. Then it takes a flag telling it that it's a shared semaphore, and then it takes the initial count of the semaphore. So we want to set it to 1, since it's going to be working like a mutex. So in this case, we're using a semaphore, but since we are sharing it among multiple processes on the same system, we set the count to 1, so it kind of works like a mutex. So when we grab it, the count goes to 0. When we give it, the count goes back to 1. And then we also save the file descriptor, and that's it for a creation stage. And then we have these methods that get and set the different variables. So basically, getting and setting the variables inside this object is synchronized using the semaphore. And we can use the same functions both on the server side and on the client side. Is this clear so far?
Yes, Martin, yes.
Yes.
So, hello, Kival. Welcome. So on the server side, I've created this C++ application where I create the simulated Verilog object and also the vCounter object, which is going to be shared. And also it has its own semaphore for the sake of the timer. So the way that timers work in Linux is you can set a timer to generate a SIG-RT signal. There are I think there are 32 signals available to you, but basically the range can vary, and it's defined to be between SIG-RT min to SIG-RT max. So anything there in between you can use for your real-time signals. And I'm using the first signal that's available to me, which is the same as SIG-RT min. And the first thing I do is I create a SIG action. I define a signal action, and I set this to be the timer interrupt, which I have here. And this is a function that's going to be called as a signal. So when the timer expires, the signal will be sent to my application, and anything that's running in my application will be interrupted by the signal. So I want to keep this as short as possible, and I'm simply going to be using this to clock the hardware so that I get a steady rate of clock for the hardware. I could have used, for example, usleep to sleep for a number of microseconds to set the frequency of the clock, but that wouldn't be exact. When I have a timer that is an interval timer, the timer will simply continue and it will fire at regular intervals. So it's a lot better. It's a lot more precise, and every time the timer expires, the signal is going to be called. And then I will clock the hardware by toggling the clock line to 1, and then evaluating the hardware, and then toggling clock back to 0 and evaluating again. And the other registers of the hardware are going to be synchronized separately. So that is going to be done as part of the main function here, where we synchronize to the timer event, and then we simply synchronize the data with the shared memory here. So to set up the timer, the first thing I do is I create the SIG action. I then empty the signal mask of this SIG action using SIG empty set with the SA mask parameter of the SIG action structure. Then I set SIG action for the SIG-RT min. So now I assign the SIG action to the signal SIG-RT min. And when this signal is sent to my application, the SIG action is going to be called. The next thing I do is I want to temporarily disable the signal when I configure the timer. So I'm going to start the timer, and once the timer is running, I'm going to enable the signal so that I start receiving interrupts. So this is similar to disabling an interrupt and then doing configuration on a microcontroller and then enabling the interrupt again. Except that we are doing this on Linux, so we're using signals. And signals are very similar to how interrupts work in hardware, except signals signals is a concept used only in software, but it kind of simulates the same thing. So I create a new mask for this signal. I empty this set. I add to this set the SIG-RT min, and I then set the process mask for the current process using SIG-proc mask with SIG set mask, and then I supply this mask to this function. So now my process is now the signal is masked out from my process. Next, I want to configure this timer. So now I want to configure this timer, and I define a structure called SIG event. This SIG event is going to be, this tells the kernel how it's going to respond to the events generated by this timer. So there's 2 ways to notify application. There is a SIG-ev signal, when it's going to generate a signal, and then there's also SIG-ev thread, which is a different way to notify. For this example, I'm going to use a signal. So we're going to be generating SIG-RT min. So I set the signal number here, which is going to be generated. So I set the way to notify through a signal. Then I set the signal that's going to be sent to my application when the timer expires. Then I set the sig value because I want to pass some local data to this signal. And here I'm going to be passing the application object, which I've created here. And the application object basically contains all the data that I'm using for my application. So I'm going to be passing this into my signal handler so that when the timer expires and the signal handler is called, it's going to get the sig info here. And the sig info is going to actually contain cval ptr, which is then going to point to my application so that I can retrieve application local data. So this shows why it's important to structure your code so that everything is in structs, so that you can pass things around easily. So I've defined my sig event to be generating the sig_rt min, and I've supplied all the configuration, and then it's time to create the timer. So I create the timer ID. It's a variable. I define the timer ID where I'm going to save the timer ID. Then I use timer create to create this timer. And I'm going to be using clock real time because I want to have a time that doesn't jump, that is that is a monotonic real-time clock. I'm going to provide this sig event definition as the second argument and the timer ID, where the ID is going to be saved as the third argument. And if this function returns non-zero, then it failed. If it returns zero, then everything's okay. So I've created the timer, but I haven't set the time for this timer. So the timer is created, but it doesn't know when it's supposed to fire. So now we have to configure the time for this timer. So I create an interval timer configuration here, and I set first the initial expiration, and then I set the interval expiration so that the timer will be reloaded, and the interval and it will then fire at this given interval. So first it will expire so this is set in nanoseconds. So this is going to be a millisecond timer. It will expire after 1 millisecond, and then it will continue to expire every millisecond. And then I use timer set time to set the time for this timer. So I use this timer ID, which I've gotten here from timer create, and I configure this timer. So now the timer is running. This is why it's good to disable the signal so that we have full control of when we want to re-enable this timer interrupt or the timer signal that I've defined above. So now it's time to enable this interrupt. So we start receiving notifications, and for that I unblock the masked signals. And after we are done here, the timer is now running, and we're receiving timer notifications. So our hardware is now being clocked. It's being clocked with a 1 kilohertz clock, so it's constantly running, and it's running at a steady pace. And now we can go into this infinite loop in main application, where we just synchronize between the hardware and the shared memory. So to do that, I lock the semaphore for the shared memory, and then I just do the exchange of values between the shared memory and the hardware. So as we run this loop, we also want to synchronize to the timer so that we don't get a tight loop here. And for that, I use a semaphore, which I give in the timer interrupt here. So every time the timer expires, I post this semaphore, and then I get this semaphore back in the main loop here, so that we don't waste CPU cycles doing this reload too many times. So we will sleep and wait for the timer to expire, and then the timer expires, the hardware is clocked, and then we can do the exchange. And so this process repeats and repeats and repeats. So this is the simulation part, and this runs as a separate process, and it just simulates the hardware. Now we can write a client which will map this hardware registers into the process address space of the client application, and then the client application can use this device as though it was basically a device on a microcontroller. So you can access those registers directly, but we're going to be using our accessor functions so that we get proper synchronization between applications. And we can actually have multiple applications accessing this hardware at the same time. So I will go to the client application here, and the client application is really simple. So we simply need to create our counter inside the client application. We pass false because we don't want to create this shared memory file again, and then we configure the output compare 1 and 2. We configure the reload, and then our counter is running and it's reloading at regular intervals, so we can just enter into a loop and just print out the information about the counter. This is what we get then. We can actually run this at a higher pace. So let's say we want to run it at 10 milliseconds, and this will just run forever. So we can start the server, and then we can start the client, and we can see that the counter is running. And it's generating 2 PWM waveforms, as you can see by 1 and 0 outputs here. So this is how you can use shared memory and timers on Linux, and this is how you can also simulate Verilog hardware on Linux and kind of make it easy to use and make it possible to create simulated hardware that you can then write code that uses the simulated hardware as though it was microcontroller hardware. So, any questions?
Yes, Martin. So I would like to know that if I'm not wrong, so can we program the same Verilog into some FPGA and kind of get the same output from it?
Yes.
Or we can interact the same way we are doing it here?
Yes.
Okay, thank you.
So that's kind of the whole point. You can take a Verilog file and compile it into C code. So using Verilater, Verilater is a compiler that generates C++ code from Verilog, and it's used for simulation purposes. But you can also use it to you can take that generated file, the generated device, and basically just instantiate it inside a process and share the state of that device with other applications on the system, so you can run simulations against that device from other applications on the system.
Yes. Okay.
So what do you find most interesting in this example?
So for me, I think this simulation part was new for me. I was not aware of it. So it was interesting. It's great.
Do you mean the part about signals, or do you mean the part about Verilog?
No, I mean the Verilog part, and it's simulation that we can do virtually.
Yeah.
I mean, we can do on the same system.
So you can see this is the visualization of this Verilog code.
Yeah.
Yeah, Verilater is really useful. Verilater is part of Icarus Verilog, and it's a simulator for C++, basically. So you can see the full command here. I first call Verilater to compile the counter.v, and then that generates a bunch of files in object directory. And then I just link that with a simple application. And then the client is here.
Yes.
So I'm just including the C file here on purpose because it's just easier for a simple make file. I have a very simple make file that just converts C files into executables. So that's just for convenience. And this is the shared memory.
Yeah.
Kind of like a shim object for the shared.
So can we try the same server code in CPP and try the same with threads?
Well, you're essentially using two threads, which are two processes
Yeah.
in this case. So you have your
Yes.
server process that runs the simulation. That
Yes.
process has a timer that clocks the hardware,
Yes.
and that process also synchronizes the hardware with the shared memory.
Yeah.
And then you have a client that synchronously accesses the hardware using the shared semaphore
Yes.
to access the hardware and read out the values and also write values to it.
So yeah. So I want to ask in that can we try the same in CPP and with the application of threads, not semaphore. I mean the mutex.
So in this case, I'm using a semaphore like a mutex, but the reason I'm using semaphore is because I'm using a shared resource.
Yeah. Shared space. Yeah. I know. Yeah.
So it would be exactly the same if you use a mutex, except that you will just use a mutex and you will lock it and unlock it.
Yeah.
But except you don't even need to use the mutex. You can use the semaphore anyway, even if you're using threads.
Yes.
It doesn't really matter.
Yeah.
You have a separate thread that runs the client. We can put the client into a separate thread in the server.
Yeah. So here it's like we are interacting between two processes and one shared space, right?
Yes.
So yeah, in that case, it will be like one process and in between two threads.
Yeah, exactly. So we could do like this. Let's see. We could put a thread here in our counter process.
Yeah.
And then we can basically just copy the client code here.
Yes. Okay.
So now we would have a separate thread here.
Yes.
That prints out the output. Does that make sense?
Yeah. Absolutely, I agree that.
Let's see. We're gonna run v counter. Yeah. So now we're running the same program. We're running in two different threads.
It's great.
And you can see that it counts to 1,000 in 1 second.
Yes.
Yeah. So one thing to notice here is that when you write your code in an object-oriented way like this, so you have an interface for the vCounter object, and it's clearly defined here with a struct vCounter for this object. It's really easy to extend your application to be multi-threaded. and it just works really naturally. You just add a semaphore if you
Yes,
need to
yes.
synchronize, and then you can synchronize accesses to that data, and it just works out really well.
Yes.